In the last video, I talked about sampling variation and that we need inference statistics to try to say something and see if what we find, like an average, for example, is in line with what we find according to some distribution, like the null distribution, for example, and then we need to have use estimated values for that. So the problem is we do not know our population values, right? So ideally, what we do is we define a distribution, and then we see is what we find in line with that or not, but we don't know the distribution, right? We don't know what the real distribution looks like. So how do we then know if our findings are in line with the alternative hypothesis? Well, that's something that we can't really do, right? So our alternative hypothesis is not usually, it's usually just H1, the effect, let's call it mu, is not 0. It's not like it's 0.5 or 0.2. If we have that very specific hypothesis that it's some value, then we could test against it, of course, but we don't usually have that. This is a really vaguely defined hypothesis. Luckily, H0, our null hypothesis, is very clearly defined. Mu equals 0. There we do know the mean, which is nice. So we don't need to estimate the population value. We know it, it's 0. What we can do, we can try to see, okay, maybe we don't really know H1. We don't really know the alternative hypothesis, but we can try to see, can we reject the idea that the null hypothesis is true? That's what we call null hypothesis significance testing. Where we pit H1, basically saying is not 0, against a null hypothesis, where the null hypothesis means, okay, the effect we're trying to reject. So null hypothesis is better defined, and it doesn't require us to know all the population values because they are fixed to a specific value, maybe 0, especially the mean. For example, the difference between two means equals 0, or the correlation equals 0, or the first regression effect equals 0, etc. It doesn't have to be 0. It could be some other value that you're interested in. For example, the proportion is not 0.5, but often it's 0. We reject H0, our null hypothesis, if our observed sample parameters, like the sample mean, take on such extreme values that they were unlikely to occur under the null hypothesis. And this is the core idea in null hypothesis testing. So it's interesting because, and this is why the Bayesians can disagree with this as well, but we are interested in H1. H1 is our alternative hypothesis. This says, okay, we hypothesize an effect is not 0. It's something. There is a relationship. But since it's hard to look at that, we don't know what it is. We look instead at trying to reject H0. And we say, okay, we first look at the null hypothesis, and if that's rejected, we accept the alternative hypothesis, which is the idea here that we're going to do. So after defining a null hypothesis to test, we can gather some data. And this data we can use to form a test statistic. The test statistic is basically a way to summarize the distance, the effect that you have in your data. So the test statistic is a standardized statistic that captures the effect of interest. For example, the distance from the mean in standardized units. Usually they take some form like ZT, chi-square, F, R, right? They have some name, usually a Roman name. A chi-square actually is also sometimes called x squared, and the chi-square is actually the distribution, but people tend to call it chi-square anyway. Test statistics always have a form of a signal to noise ratio or effect to error ratio. So basically, there's some effect, some signal, let's say effect, some distance from the mean compared to how much uncertainty there is. After forming a test statistic, we can use the associated null distribution to determine how likely our observed test statistic was under the null hypothesis. Right, so we don't actually look at the distance between means, we look first at the standardized unit, z-scores if we can, or otherwise t-scores. And later we're going to use f ratios as well. Because we know these distributions have defined distributions, and we can look at the probability. We can do it in JASP, right, or the software will do it for you. We understand their probability and how they work. All right. So let's say we have t, and t is a test statistic of interest. This could be, I could use capital T to make sure it's not lowercase t, so test statistic. It could be anything like a t or z or f or anything really, or r, your correlation. right? Anything. So then we define two things: the observed value of the test statistic and the value under the test statistic under the null hypothesis, which is usually just 0. The p-value, which you obtain from the null hypothesis, is then the probability of observing a test statistic at least as extreme as the one observed, given that the null hypothesis is true. Okay, and that actually depends on your hypothesis, which is a bit weird. So if your hypothesis, I hypothesize that the test statistic is not 0, right? T0 would then be 0 in most cases. Then the p-value is the probability of obtaining a test statistic higher than what we observed or lower than the negative value actually, what we observe, given that the null hypothesis is true. So basically what it means is we have a distribution. Maybe we find the test statistic here. We're interested in this area here, the probability, and a corresponding area on the left side. If you have only a directional hypothesis, like you expect the effect to be in a certain direction, higher or lower, then you just look at the probability above or below your observed value. We reject the null hypothesis if alpha is the p-value is lower than alpha. Usually that's 0.05, basically meaning that if the pattern that we found in the data, or more extreme, was less than 5% likely to occur under the null hypothesis, we say, okay, it's quite unlikely it would have occurred if the factor is 0, so we deem it significant. It does mean that we also expect to erroneously reject the null hypothesis about 5% of the times, if there is no true effect, right? So that's really important. 5% of the times we're going to get a significant effect. So that means if I run 20 studies, I'm going to get one significant by chance alone. That's why it is absolutely vital that we do more studies and we replicate things, because there was a 5% chance that we got some effect. So yeah, it could be that if I run 20 studies and I publish 5% of those, then I was published significant effects, but they're all not true, right? So you want to replicate it, try again. If you then replicate effect 3-4 times, then you would be really, okay, yeah, this is something. The p-value is furthermore only correct when performing the test exactly as planned. Now I'm going to talk more about this later in this course. This is really important to already understand now. This p-value is based on certain assumptions. It's based on the idea of this probability distribution that we know from this test statistic. Like T or Z or F, it has a certain probability distribution. That probability distribution is only valid if we do the test as we planned. What I mean with that, I'll discuss it more later in the course, but what I mean with that is, for example, it's depending on the sample size distribution. The higher sample size, the smaller the distribution. But what it doesn't take into account is if you had some sort of variable sample size. So let's say I collect first 50 people, I look at the data, I see it's not significant, I collect 10 more, and then I look at the data again, and see it's significant, so I stop. In this case, this p-value is not valid anymore, because the p-value did not know you were going to first look after 50 and then collect more, and then look again. And maybe if it wasn't significant, collect 10 more people. If you keep doing that, at some point, we might get a significant effect by chance alone, higher than 5% chance. And I'll talk more about this later in the course, but this is something really important to keep in mind. All right, so here's a comic again from XKCD. Again, it's a great source of very nerdy comics. And we have this girl here, says jelly beans cause acne, which you probably heard on the news, TikTok. And then the guy says, scientists, investigate. The scientists are playing Minecraft, but yeah, okay, they need to investigate, so sure. So these are scientists. You can see that they wear like sciencey goggles, so that's why they're scientists. And they say, we found no link between jelly beans and acne. So they got a sample of people. Did they eat jelly beans? Did they have acne? Is there a correlation between them? There was a p-value of higher than 0.05. Or maybe that you gave a group jelly beans to eat and a group not, and then you look at their difference in acne, for example. Higher than 0.05, so it's not significant. Then this girl said, but I hear there's a certain color that causes it. And they want to play Minecraft, but okay, we're gonna investigate more. So the scientists look at all the colors. They found no link between purple jelly beans and acne. They found no link between brown jelly beans and acne. They found no link between pink bean, etc., 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 etc. 20 in total. And by chance alone, well, you don't know by chance, of course, but they find a link between green jelly beans and acne. Now, this is something you would expect by chance alone, of course, because that's how we accept the null hypothesis. So what you shouldn't do is then write a newspaper about green jelly beans linked to acne. The 95% confidence, only 5% chance constant, right? Because it doesn't take into account. It doesn't take into account that there were actually 19 other tests performed as well. All right, so let's look at the logic of null hypothesis testing. So let's say here we have a scale. What is the x-axis? Or in this case, let's say it's a correlation. Like we have R, correlation. And let's say we observe two different tests. We have one where the correlation is 0.3 and where the correlation is 0.1. So are these significant or not? Right, we find a correlation in the sample. We know they're not going to be 0 because it's a sample, but is it near 0 enough? So we first need to define the null distribution, the likelihood of finding a test statistic if the true effect is 0. And after we define this distribution, we then look at this distribution, okay, from which point on is the area 5%? From that point on, we deem stuff significant. In this case, this one is not significant, but this one is significant. How do you look at this? Well, in JASP, you can just get this. You can do normal distribution and say, okay, or whatever distribution you have, 5% on the right tail side. Typically, if this is a Z score, like 1.96, if it's T score, it's also around 2 or so. We can also calculate the p-value. In this case, we had a one-sided effect. Maybe, so we look at this area to the right of what we observe to get the p-value. For the blue one, it's not significant. For the red one, it is significant. And that's really the idea behind null hypothesis testing. Now in PL2131, if you studied that before at NUS, you learned about some common null hypothesis tests, which include the Z-test and the T-test. The Z-test is used for testing a difference in a mean where you know the standard deviation. So for example, you could test, okay, I know from the general population what the standard deviation is, what the distribution is of a variable. So let's say I know the average height in Singapore is, I don't know, something with a certain standard deviation. And now I want to see in a sample, are they actually deviating from that height significantly? Then we can do a Z-test for that. Often, you don't know the standard deviation. So if you do a null hypothesis test, okay, we set mean to 0. So yeah, sure, okay, right? And we assume it's normally distributed. So we have a mean and we have standard deviation. This one we know, so we don't need to estimate or anything. But this one, yeah, we don't know. We don't know the standard deviation. So then we have to use this t-test, which we get, which is basically the same as a z-test, but slightly different. The t is just a little bit like more like skewed here, like slightly different shape. That we can use if we have to plug in our sample estimate of the variance for, or the standard deviation for the real standard deviation. Then you have things like a one sample t-test, independent sample t-test, and paired sample t-test. Now we're not going to look at those in this course. We're going to look at something we call ANOVA, which is basically the same, but we will see these test statistics a lot for parameters in the model, which is also using the same logic. You have seen also chi-square test for testing association between categorical variables. This looks at if like levels of two discrete categorical variables is there a relationship between them. And the correlation test for testing association between continuous variables. And to these you probably already know. In this course, we're going to look at mainly regression analysis. We're going to look at F-tests for comparing two regression models, hierarchical regression models. We're going to look at ANOVA for comparing models where we have a categorical predictor. And turns out that's just a hierarchical regression model, so that's also an F-test as well. Right, that's it for this video.